We're given a carrier signal and a modulating signal, and we ask what the mathematical expression for the AM modulation signal is. Well, we start with a template, right? An expansion for the AM modulation signal that is given by the carrier signal plus the peak voltage of the modulating signal over 2 times cosine of 2 pi of the carrier frequency minus the modulating frequency times t plus the peak voltage of the modulating signal times cosine of 2 pi times the carrier frequency plus the modulating frequency times t. So we have one tone that has the carrier peak voltage and has the carrier frequency. Then we have two tones that have the same power levels, same magnitude, the same coefficient, but they are placed apart by different frequencies, right? By the difference between the modulating frequency and the carrier, and the second, the third tone here is the frequency is the carrier frequency plus the modulating frequency. So let's plug in our given signals into this form. So we have that the amplitude modulation signal is given by 300 cosine of 2 pi of 10 to the 7 times t. Okay, plus even max, which is the peak voltage, 200 volts there. So it's 200 over 2 times cosine of 2 pi of the carrier frequency 10 to the 7 minus the modulating frequency 10 kilohertz, right? So we have 10 megahertz minus 10 kilohertz. Another tone that has a peak voltage of 200 over 2 times cosine of 2 pi of 10 megahertz plus 10 kilohertz. Okay, and we can now solve for give the more precise values here, simplify the expression a little bit. So we have the amplitude modulation signal is equal to 300, the carrier, 300 cosine of 2 pi 10 megahertz times t plus 100 cosine of 2 pi of 10 megahertz minus 10 kilohertz is, we have here the spectra output for the modulation signal, we have 3 tones. One is the carrier at 10 megahertz, and we have a lower sideband and an upper sideband. The lower sideband frequency is given by the carrier frequency minus the modulating frequency, which is 10 megahertz minus 10 kilohertz, which is 9.99 megahertz. So that's what goes here. So we have 100 cosine of 2 pi of 9.99 megahertz t plus 100 cosine of 2 pi times the frequency for the upper sideband, which is 10 megs plus 10 kilohertz, and then again we have the frequency carrier for the modulating frequency is 10.01 megahertz. Okay, and also we can do it from here. So we have that 10 megahertz plus 10 kilohertz is equal to that. And we go to engineering notation. That is 10.01 megahertz. Times t. And that is the mathematical expression. So we have a signal, a carrier signal that is as it comes, and then we have 2 tones, one for the upper sideband, for the lower sideband, because we have the frequency is lower than the carrier, and we have an upper sideband, and that has a frequency that is higher than the carrier. Okay, and as we know from Fourier series expansion, each component represents a tone, and that is reflected on the spectra. So we have a carrier at 10 megahertz. We have a lower sideband at 9.99 megahertz, which is right here. And we have a upper sideband carrier, an upper sideband that is at 10.01 megahertz. 3 tones, which corresponds to the amplitude modulation signal. Carrier plus a lower sideband and upper sideband. And that's all.